All right, let's dive into neutrino detection. We're talking ghost particles here, billions passing through us every second.
It really is mind-boggling.
So today we'll explore how scientists actually detect these tiny things. You sent over some awesome resources, by the way. The Wikipedia entries on IceCube and, well, neutrino detectors in general, plus an article on all the different detection techniques.
Yeah, it's a real challenge, detecting neutrinos pushed physics and engineering to their limits. But before we get into how we catch them, what do you say we do a super quick recap of what neutrinos even are, for our physics student listeners?
Good point.
Okay, so they're subatomic particles, tiny, practically zero mass, and no electric charge.
Which I guess makes them super hard to detect, huh?
Exactly, because they barely interact with matter. Think of it like trying to catch a snowflake in a blizzard.
Wow, okay, yeah, that's a pretty tough challenge.
It is, but scientists are clever, right? They've come up with some seriously ingenious methods over the years.
Let's start with one of the first then, scintillators, right?
Right, scintillators are these materials that give off a tiny, tiny flash of light when a neutrino interacts with them. Kind of like the neutrino leaves a little footprint behind.
Okay, so the neutrino bumps into something in the scintillator and boom, a spark of light.
Exactly, and even though it's incredibly faint, we can amplify it with these super sensitive instruments. They're called photomultiplier tubes, so we can actually see evidence of the neutrino interacting.
Clever. Isn't that how they detected the first antineutrinos, by the way?
The Cowan-Rains experiment.
Yep, that's the one.
Yeah, they used a big tank of water mixed with cadmium chloride, which acted as the scintillator. It was a groundbreaking experiment, proved antineutrinos existed, opened up a whole new area of research in particle physics.
And we still use scintillators today, right?
Absolutely. Modern detectors like Camland in Japan, they use them to study antineutrinos from nuclear power plants.
Okay, so that's one way. What other techniques are out there?
Well, there's radiochemical methods. Instead of looking for light, these detectors use, well, the transformation of one element into another. That's how they know a neutrino interacted.
So the neutrino hits an atom and poof, it changes into a different element. Like alchemy, almost.
Haha, that's a great way to put it. The classic example is the homestake experiment. They used a huge tank of perchloroethylene, the stuff they use in dry cleaning.
Buried deep underground. Why bury it, by the way?
To shield it from other particles, those could mess up the results. Anyway, neutrinos interacted with chlorine atoms in the fluid, changing them into argon atoms. Then they could extract and count the argon atoms to measure how many neutrinos interacted.
And that's how they first detected solar neutrinos, right?
Yep, although it caused some head scratching, too. They found way fewer neutrinos from the sun than expected.
The solar neutrino problem, right?
You got it. Showed us that an experiment designed to answer one question can lead to even more questions.
Mysteries on top of mysteries.
Exactly, but to solve that mystery, we needed a better understanding of neutrino oscillations. That's a topic for another deep dive, though.
All right, fair enough. So we've got scintillators, we've got radiochemical methods. What other tricks do you physicists have up their sleeves?
Let's talk about Cherenkov detectors. They're some of the most visually stunning neutrino detectors out there.
I've heard of those. Don't they involve detecting, like, a special kind of light? One that's produced when particles go faster than light in certain materials. But doesn't that, actually break the speed of light?
You're right. Nothing can travel faster than light in a vacuum. But in a medium like water or ice, light actually slows down. So when a charged particle, like, say, a muon created by a neutrino interaction, goes faster than light in that medium, it emits a cone of bluish light. It's called Cherenkov radiation.
Like a sonic boom, but with light.
Exactly. Cherenkov detectors, like the famous Super Kamiokande in Japan, are basically giant tanks of ultrapure water surrounded by thousands of super-sensitive light sensors. When a neutrino interacts with the water, it can create a muon, which then zips through the water, emitting Cherenkov radiation, and boom, the sensors pick it up.
So they're not directly detecting the neutrino itself, but the aftermath of its interaction.
Exactly. And here's the cool part. By analyzing the light pattern, they can reconstruct the path of the muon and get clues about the direction and energy of the original neutrino. It's like a cosmic CSI investigation.
That's incredible. So then that brings us to, I guess, what's the most mind-blowing neutrino detector ever built? The IceCube Neutrino Observatory.
Ah, yes, IceCube, taking Cherenkov detection to a whole other level.
I mean, come on. A cubic kilometer of Antarctic ice with over 5,000 light sensors embedded in it, buried deep beneath the South Pole.
An incredible feat of engineering, for sure. And the principle is similar to Super Kamiokande. When a high-energy neutrino interacts with the ice, it can create a muon. The muon emits Cherenkov radiation, and those 5,000 light sensors are constantly watching for those telltale flashes. And by analyzing those patterns, scientists can trace that neutrino's path back to its source. potentially pinpointing the locations of distant black holes or supernovae.
That's amazing. So they're using neutrinos to map out the universe's most extreme events?
Exactly. Now, these three techniques, scintillators, radiochemical methods, and Cherenkov detectors, they're the main ones. But, there are other less conventional methods being explored too.
Oh, really? Tell me about those. What are these, like, unconventional methods?
Well, one is radio detection. So this technique looks for radio waves emitted when high-energy neutrinos interact with matter. There's this project called ANITA, the Antarctic Impulse Transient Antenna.
Wait, so instead of light, they're listening for radio signals.
That's right. ANITA is designed to detect those signals from high-energy neutrinos hitting the Antarctic ice sheet. It's a pretty unique approach.
Sounds like it. What other approaches are they using?
Another one is using tracking calorimeters. These detectors use layers of dense material interspersed with detector material, and they track the paths of charged particles created by neutrino interactions.
So it's like a multi-layered obstacle course for particles.
Aha, good analogy. As the charged particle moves through the layers, it loses energy, right? And the detector materials record those energy losses, so scientists can reconstruct the particle's trajectory.
And from that trajectory, they can work backwards to get information about the original neutrino.
Exactly. See, each technique has its own strengths and weaknesses. Scintillators, they're great for detecting antineutrinos from reactors, but they don't really tell you much about the direction the neutrino came from. Radiochemical methods give you a really precise count of neutrino interactions, but not much about their energy or direction.
Right, and Cherenkov detectors, they're excellent at giving you directional information and energy estimates, which is why they're so useful for those astrophysical observations, right?
Precisely. But they usually need massive volumes of material, like, water or ice, to increase the chances of a neutrino actually interacting.
And then you have those more specialized techniques like the radio detectors, which are super sensitive to ultra-high energy neutrinos, and the tracking calorimeters, which are better suited for studying high energy neutrinos from accelerators.
It all comes down to choosing the right tool for the job, right? Depending on what you're trying to study about neutrinos.
Yeah, that makes sense. But with all this work going into detecting neutrinos, why are they so important? They're practically invisible. They have almost no mass. They rarely interact. Why are physicists so interested in them?
That's a great question. Neutrinos give us this unique window into some of the most powerful and mysterious things in the universe. They can travel incredibly far without being disturbed, carrying information from the cores of stars, from supernova explosion, even from the Big Bang.
Wow, so they're like little messengers from these extreme environments out there.
Exactly. And by studying them, physicists can learn all sorts of things about what's happening inside stars, the mechanisms behind supernovae, and maybe even stuff about dark matter and dark energy.
It really sounds like they're a key piece in understanding the universe.
They are. And as we develop even more sensitive detection techniques, we're bound to find even more cool stuff in the years to come.
It's amazing to think that such tiny particles have so much to tell us about the cosmos. You mentioned that neutrinos could even tell us about the Big Bang. What can you tell us about that?
Sure. So the Big Bang, the event that, started the universe, produced a huge number of neutrinos. These are called relic neutrinos. They're still out there, permeating space.
A cosmic echo of the Big Bang.
Exactly. Detecting them would be incredible, right? It would provide direct evidence of the Big Bang and give us valuable information about the early universe.
I can definitely see why physicists are so eager to find them. But if they're from the Big Bang, wouldn't they be super faint and difficult to distinguish from other neutrinos?
You're absolutely right. It's one of the biggest challenges in neutrino astronomy. They have incredibly low energies and hardly interact with matter at all. We'd need super sensitive detectors and sophisticated techniques to even separate them from the background noise.
That's quite a challenge.
It is. Scientists are looking at a lot of different ideas and technologies, like ultracold detectors, or looking for certain signals in the cosmic microwave background radiation.
The hunt for these ancient messengers from the Big Bang continues then.
It certainly does. And who knows what secrets they'll reveal about the birth and evolution of our universe.
It really is amazing. Studying these tiny, almost invisible particles can tell us so much about how the universe works.
It shows you how connected everything is, right? From the smallest particles to galaxies and those massive superclusters.
And for all those physics students out there, I hope this deep dive into neutrino detection has, maybe sparked some curiosity, inspired them to explore neutrino research a bit more.
It's a field with so much potential, so many challenges and opportunities. And there's just so much more we can learn about neutrinos and what they can teach us about, well, reality itself, I guess.
Well said. Every time we learn something new about neutrinos, it seems like it just leads to more questions.
That's science for you, right? It's this never-ending search for knowledge. And neutrinos, with, their mysterious nature and how they connect to the cosmos, will keep physicists busy for a long, long time.
So to all our listeners, whether you're, deep into your physics studies or just fascinated by the universe, keep exploring this world of neutrinos.
There's a whole universe out there waiting to be discovered, one tiny particle at a time.